Hi, my name is Matthew Dufili, and I'm presenting on behalf of the UMBC Robotics team for the Student Unmanned Aerial Systems competition. This was UMBC's first year competing in the competition, and in this presentation, we will outline how our first year went and just our general design process. Our development team consisted of 7 members, mostly juniors and seniors, and mostly mechanical engineers, but there were also a few computer science students. Most of us have had experience with either like FIRST Robotics, FRC, and FPC, or building drones or RC planes on our own time. However, that drone and plane experience wasn't really with autonomous systems, so there was still stuff for us to learn during the competition this year. The team found that the biggest constraints in the competition rules were the flight distance and time requirements, as well as the requirement of having to redo waypoint missions after landing. So if the drone needs to fly 12 miles in 30 minutes, that's a minimum speed of 24 miles an hour. And that only includes just flying. That doesn't include the time to find targets and to drop the water bottles on the targets. So realistically, the aircraft would have to fly 30 miles an hour and probably even faster than that. If we were to decide to take multiple trips, that speed would go up even more because we would need to refly the 12-mile waypoint course and we wouldn't get any more time. Um, Additionally, we wouldn't be able to swap out our batteries, so um, depending on what type of aircraft we chose, the battery life could vary to being like really good or just not good enough to fly another 12 miles. So comparing multi-rotors and fixed-wing aircraft, fixed-wing aircraft have superior range, efficiency, and cost because um, fixed-wing aircraft usually have like 1 or 2 motors as opposed to like 4 motors on a drone, and also because of that, there's less electronics that have to go onto it. On the other hand, multi-rotors are much more maneuverable than fixed-wing aircraft, and they're a lot easier to manufacture because you don't have to cut out foam to precise shapes to get the airfoil shape you want. And also, if planes crash, they also do tend to be a little bit more difficult to repair. So the team decided that the maneuverability was much more valuable to us, especially when it comes to programming, since it would ease finding targets and flying over them and dropping the water bottles with the targets much easier. We decided to go with a multi-rotor design. As mentioned before, multi-rotor systems can get much more expensive than fixed wings, and the drone that we designed and wanted to build was going to cost about $9,000, but we were unfortunately unable to secure the funding for that drone. So currently, the only functional drone we have right now is a smaller prototype drone. We'll come back to that prototype drone and talk about it a little, but the next section will be about our design process for the larger drone. So the parts we picked out for the bigger drone included a Pixox 6C for the flight controller, T-motor, 120 kV motors, 120 amp 12S ESCs, 30-inch propellers, a Foxtech frame which is 1200 millimeters, 31,000 milliamp hour 6S lipos. The plan was to have 2 batteries in series to get 12S, to get a simulated 12S pack, and then put 2 of those in parallel. So we'd essentially have two 12S batteries in parallel. For the telemetry radio, we were going to use a SICK 950 megahertz radio. And for the receiver and transmitter, we have a FrSky QX7 and a FrSky Access Archer R8. Here we just have a estimation of what the drone was going to weigh. On the very far right, we have our factor of safety column where we just said worst case scenario, each part is 110% of the weight that we're expecting it to be. And that total weight came out to be 53 pounds, which is just about 2 pounds short of the limit. When it comes to the motor, the U12-2 was in the sweet spot of all the motors we found. We were researching motors from September up until December and even January, trying to look at all of our options. All the other options that we saw either had like too low of a thrust to weight ratio, or they did have a high enough thrust to weight ratio, but we did not have enough flight time. We were using an online calculator to find all these values because they have a database of pretty much every consumer drone motor, ESC battery that you can think of. And whenever you give it the parts that you want to use, it'll run calculations on the amount of power it'll consume, how much thrust it'll have, the estimated flight time, and a bunch of other useful data. So based on those motors, T-Motor recommended on their website that we also picked the 30-inch propellers and 120 amp ESCs. And with this selected combination, we would get a 2.3 thrust to weight ratio with about a little bit over 30 minutes of mixed flight time and a top speed of 45 miles an hour. Here's a sample of the sort of data we would get from the drone calculator. As you can see, it has all of the information like the thrust weight ratio, how much power it consumes, how much time it can stay in the air of like hovering or mixed flight time. We did take this data with a grain of salt, especially because this software was mainly created for use with RC planes and was eventually ported over to be used with drones, but some of the calculations, especially the range calculations, aren't as reliable as the plane ones. Here we have our full CAD model of the larger drone. It has the payload mechanism, where the electronics will be mounted, as well as how we would mount the 4 batteries onto the drone. The team selected this frame because with 30-inch propellers, the minimum size that the frame would have to be is 1100 millimeters, and this one's 1200, so it meets that requirement. And as advertised, this frame can support carrying cameras below it, as you can see in the picture, and we wouldn't be using a camera of that size. We'd be using a smaller one for the image processing. We'll get into that later. But we would also put the payload mechanism underneath. The frame is also advertised to be used with coaxial motors. However, we would only be using 4 motors instead of the 8 because we don't need the additional thrust of 4 extra motors. Here's the 3D model of the completed payload mechanism with the water balls attached and the release mechanisms on top with the servos. Water ball weighs about 1 pound, so each portion of the payload mechanism would have to be able to support that weight. The mechanism has an easily removable clip as per the competition requirements for the judges to be able to remove the clips and get the water ball back fairly easily. To ensure a safe landing, each water ball will have a 4-foot diameter nylon parachute. And to release the water balls, there will be a string from the top of the bottle that will loop around a pin that will get released by a servo. Here's just a cross section of what the clip is going to look like around the water bottle. So each portion of the payload mechanism will just be a duplicate of each other. They will have 9-gram servos, which have a torque of 1 kilogram per centimeter, and attached to the servo horn will be a rod that will also be attached to the locking pin that holds onto the rope that's attached to the water bottle. And when the servo turns, it'll pull the pin out of the way of the rope, and then the water bottle will be able to fall. In the conical section right above the water bottles, there will be space to store the parachutes before the water bottle is dropped. Not including the water bottles, the payload mechanism weighs a total of 1.6 pounds. So the order of the autopilot sequence is as follows. First, from the ground station, we will upload the GPS waypoints provided by the judges, and then once we are ready to fly, we will swap the quad to mission mode, and it will follow all the waypoints. Once the mission mode is finished, we will then switch to offboard mode, which allows external devices such as a Raspberry Pi to control the drone's movement. We'll get more into that later. And the Raspberry Pi will tell the quad to find a search pattern as it looks for a target through a camera. Once a target is found, the Raspberry Pi will tell the drone to get directly at that target to verify that it is a proper target. And then once the drone is directly above it, the Pi will then control one of the servos on the payload mechanism to drop the correct water bottle. After the water bottle is dropped, the Pi will then tell the quad to go back into that search pattern, and it will repeat until time is running out or until all of the water bottles have been dropped. The autopilot software that we chose is PX4 because our club advisor and also a company that was helping mentor us had experience with it. So if we ever needed any help, then we could just ask them and they'd be able to answer our questions. In order for the Raspberry Pi and for our ground station to communicate with the flight controller, we will be using the Mavlink protocol. It's built into the Pixhawk and it's pretty straightforward to use. Using Mavlink, we will be able to upload the GPS waypoints from our laptop through the telemetry radios and then tell it to start flying the mission. For the Raspberry Pi to control the drone through Mavlink, it will be using Python and the Mav SDK library. That code will be able to detect whenever the mission is finished and then go to offboard mode and perform the search routine. To test some of the autopilot code, we were using the Gazebo simulation software, and we were able to interface Q ground station with the autopilot simulation as if it were the actual drone. We were also able to get a fake GPS plugin working with the simulation so that we can make the drone think it's at St. Mary's Airport when it's actually just running on a computer. We were able to use Q ground control to see that the drone did think it was at St. Mary's, and then we could give it different GPS locations around the airfield as if it were actually there. We were also able to get the Python code to give simple commands to the drone running in the simulation and put it into offboard mode and have it fly to different points of the airfield in that mode. Using the Python code, we were also able to put the geofence into a text file and free that text file to get all the GPS locations to make the fence polygon and then upload that to the simulation drone. And we were able to see the proper fence around the airfield through the ground station software. As stated before, we were planning on using a Raspberry Pi 3 to run our custom Python code for the search pattern and to also control the servos when we're above the targets. On the right is a suggested network topology for the drone systems. Ours is slightly different. We were planning on connecting the telemetry radio directly to the flight controller. instead of to the Raspberry Pi, but the flight controller and Pi would still be communicating over MavLink to each other. The onboard mode that the Pi would be able to use through the Python code, you could give the flight controller a velocity vector or a position to go to, or even an acceleration vector, and the drone would obey those commands and just kind of go wherever you want it to. And that would be how we would give it the search pattern. We just tell it go this velocity and just keep on telling it to do that until we find something on the camera. The Raspberry Pi will be using a camera for target detection, and it will be using the OpenCV image processing library to do all this image processing. And OpenCV is compatible with Python, so we can use Python for the image processing as well as interfacing with the flight controller through MavLink. This is one of our initial photos that we have taken with the camera. Unfortunately, we didn't quite get the chance to run pictures of sample targets through the image processing. This photo was taken at about 75 feet, just kind of based on rough calculations with like tape measures and floor tiles. These images are zoomed in from the actual image from the camera, but I can see on the right, that is our edge detection being ran through the image processing, and it does pick up the pillars on the door fairly well. Here's a 3D model for our camera mount. It will house our Raspberry Pi 3 at the top. This is just flipped upside down. The camera on top here would be facing towards the ground for obvious reasons. And there will also be a cooling fan attached, since we are expecting the air fuel to be very hot, and the Raspberry Pi will require cooling if it's doing image processing. So onto our prototype drone. So this is currently the only drone that the team has right now. We were able to acquire some of the parts from the original parts list, such as the Pixel 6C, the telemetry radios, the particular receiver that we chose, uh, but stuff like the batteries and the motors and ESCs we weren't able to get. So on this drone, the main difference between this one and the big drone we want to build is basically just the frame, propellers, speed controllers, battery. Um, the frame we got is the RC Wing CD 550, 550 millimeter frame, and that actually came in a kit with the equal power motors, the air speed controllers, and the turret propellers. We picked a smaller battery for this prototype drone, and so we picked a 4S Turnigy 10,000 milliamp hour battery. On the maiden flight of the drone, we did discover that there were thrust issues. In particular, in order to take off, the drone needed like at least 75% throttle to take off, and as we'll see in the video, as it runs through a waypoint mission we uploaded, as it tries to go from one point to another, it just falls out of the sky, and that's most likely because as it's tilting to gain some horizontal speed, it's losing some of that vertical thrust, and it just can't support itself and starts falling. 40 feet this time. Dude.
It's spinning.
Why is it spinning?
Why is it going so slow?
Whoa! What is it?
I'm taking over.
Alright. I think you're able to set.
When it came to using the ground station software to communicate with the drone, there weren't any issues at all. We were able to upload our sample GPS waypoint course to the drone, and we were also able to get telemetry back from it. For our second and final flight test, we decided to test the drone out with a smaller battery to lower its weight and see if it actually was a thrust issue. As a result, the drone actually did take off with much less throttle, about like less than half throttle. And the maneuverability of the drone also improves so it wouldn't just follow the sky when going from one waypoint to another. However, in this video, as the drone was landing, it started oscillating, and the team has thought of two possible reasons why this could have happened. The first possible reason is that the arms that the motors are attached to they weren't aligned correctly enough. So as it was coming down, the imbalanced thrust just made the drone lose control. The second hypothesis is that the PID wasn't properly tuned for the drone. The team hadn't done any previous PID tuning on the drone. We had just flown it, and it seemed to be mostly fine, so we didn't feel the need to do any tuning at beforehand.
I'm gonna take it off.
Where is it supposed to go?
40 feet, then over that way.
Holy smokes!
For so much faster. Then to the right, then it's gonna return to the landing spot.
Oh, dang you!
Dude.
Dang it.
Oh, wait.
What?
I think it goes to 100 feet before it lands.
Okay.
Yeah, it went to 80.
And it's not right above us. You might wanna move.
Yeah.
Don't fall.
Oh, is that you?
No.
Kill switch.
As a result of only having a couple days for test flying, only simple tests were performed. We didn't do any in-depth autopilot testing, especially with the Raspberry Pi. Some code was ran through the simulator, but that was just for the off-board mode as mentioned earlier. No long-range communication testing was performed. We didn't put the drone through an extensive amount of flight hours. It was probably even less than 30 minutes total. We didn't get the chance to 3D print our payload mechanism prototype or to like iterate upon it. And we also didn't do much image processing, testing. All we did was basically just the doorway example you saw earlier. This is all partially due to us spending a lot of time in the beginning of the year with the whole team researching motors and how to get the quadcopter even get off the ground and to fly for as long as we needed to. Some of our issues were partially due to funding because the drone that we had, it just simply couldn't meet the requirements that we would need to test, such as flying 1,000 feet away from the pilot or staying in the air for 30 minutes. It could barely lift itself off the ground with the big battery. So to summarize, the team designed a quadcopter to meet all the requirements of the competition, and according to our drone calculator, we felt that we did make a design that could meet these requirements. However, due to lack of funding, we were unable to build this drone, and instead all we have is a much smaller, less capable drone at our disposal. Right now, the only thing we're confident in saying that the drone can do is run waypoint missions, and for next year, we hope to learn from our mistakes, and we hope to find better ways of receiving funding so that way we can make something that we're really proud of. Once again, this was our team's first year competing in the competition, and we're all grateful for the opportunity that we've had in this competition to just make drones do cool things. Thank you for your time.